Air travel produces nearly 3% of global carbon emissions, a figure that continues to pressure, which makes sustainability is no longer a marketing slogan. It is fast becoming a non-negotiable standard for the future of the industry. While Boeing is still working to regain stability in the wake of the 737 MAX crisis, Airbus is pursuing something far more ambitious, an aircraft designed not only to reduce environmental impact, but to redefine performance expectations altogether. That vision is called ZeroE, a bold, hydrogen-powered concept that aims to achieve zero carbon emissions in flight. But what exactly is ZeroE? How realistic is it? And could it truly become the aircraft that carries us across oceans in the decades ahead? Let's take a closer look. Commercial aviation has long relied on jet fuel, a dense, energy-rich source that made modern global travel possible. But it also produces carbon dioxide, nitrogen oxides, and contrails that contribute to climate change. Therefore, the industry has committed to reaching net zero carbon emissions by 2050. The challenge is enormous. One proposed solution is sustainable aviation fuel, or SAF. SAF can reduce life cycle emissions significantly and works with existing aircraft, but production remains limited and expensive. Scaling SAF globally is a logistical challenge. What about electric aircraft? Battery technology works for small planes and short commuter routes, but for long-haul flights, the energy density simply isn't there. Batteries are too heavy. So, if conventional jet fuel must eventually be phased down, and batteries can't carry a wide body across oceans, the industry must look elsewhere. That's where hydrogen enters the game through a program known as ZeroE. But what is ZeroE? ZeroE is a groundbreaking initiative by Airbus to develop the world's first hydrogen-powered commercial aircraft capable of producing zero carbon emissions in flight. Launched in 2020, the program represents Airbus's long-term strategy to decarbonize aviation, one of the most challenging industries to clean up. At its core, the idea is both simple and revolutionary: replace conventional jet fuel with hydrogen. When produced using renewable energy, so-called green hydrogen, this fuel generates only water vapor as a byproduct during operation. In the early stages, the manufacturer explored multiple configurations. These included hydrogen combustion engines adapted from traditional turbofan designs, as well as radically different airframe concepts such as turboprop aircraft and blended wing body layouts. However, after several years of research and evaluation, Airbus announced in 2025 that it would focus entirely on hydrogen fuel cell technology. In this approach, liquid hydrogen stored at an ultra-low temperature of around -253 degrees Celsius undergoes an electrochemical reaction with oxygen inside fuel cells. This process generates electricity, which then powers a fully electric propulsion system. The current concept features 4 large electric propellers mounted under the wings. Crucially, there is no combustion involved and no direct carbon dioxide emissions produced during flight. More importantly, the latest ZeroE concept targets the regional aviation market with capacity for around 100 passengers and a practical range of approximately 1,850 kilometers. This makes it particularly suitable for short and medium-haul routes, where fully battery electric aircraft still face significant limitations due to energy density constraints. Technologically, the program has already reached several major milestones. Airbus has successfully tested a 1.2 megawatt iron pod fuel cell system, one of the highest power levels ever demonstrated for aviation applications. The company is also collaborating with MTU Aero Engines to develop scalable fuel cell propulsion systems further. Notably, a large-scale integrated ground test of the complete propulsion system, including hydrogen storage, fuel cells, power electronics, and electric motors, is planned around 2027. Earlier discussions included potential in-flight hydrogen testing using a modified A380 testbed, though the overall program timeline has since been adjusted to address technical and infrastructure challenges. However, ambition is one thing, engineering reality is another. And when it comes to hydrogen aviation, the real test begins not in concept art, but in physics. Before we go any further, take a moment to hit that subscribe button. You won't want to miss what comes next. On paper, hydrogen looks almost perfect. By weight, it contains nearly 3 times more energy per kilogram than conventional jet fuel. That sounds like a breakthrough, but energy density tells 2 different stories. By mass, hydrogen wins. By volume, it struggles. Hydrogen is incredibly light. To store enough of it for flight, it must be compressed or cooled into liquid form, and that liquid state exists at an extreme temperature of around -253 degrees Celsius. Unlike jet fuel, which can be stored conveniently inside the wings of today's aircraft, liquid hydrogen requires large, heavily insulated, cylindrical tanks. These tanks cannot simply be shaped to fit thin-wing structures. They demand space and protection, and that changes everything. It means redesigned fuselages, potentially wider aircraft bodies, reinforced internal structures to support cryogenic tanks, entirely new internal layouts for passengers, cargo, and systems. Hydrogen is not a drop-in replacement for jet fuel. You cannot retrofit it into existing aircraft. You must design the airplane around the fuel, and that is a fundamental shift in aircraft architecture. But even if Airbus succeeds in building the aircraft, another question immediately follows: where will the hydrogen come from? Today's airports are built around jet fuel, transported, stored, and distributed through a mature global supply chain developed over decades. Hydrogen requires something entirely different. Airports would need new cryogenic storage facilities, specialized refueling equipment, new safety standards, new training procedures, and an entirely new logistics network to transport and handle liquid hydrogen safely at scale. And there's another complication. Most hydrogen produced today is gray hydrogen, derived from natural gas, a process that emits significant amounts of carbon dioxide during production. If aviation simply switches to that supply, the climate benefit largely disappears. To genuinely reduce emissions, the industry would need green hydrogen produced using renewable electricity through electrolysis. But global green hydrogen infrastructure is still limited, expensive, and far from widespread deployment. Which means ZeroE is not just about building a new airplane, it's about transforming an entire ecosystem from energy production to airport operations on a global scale. Finally, there is propulsion itself. Airbus has partnered with CFM International to explore hydrogen combustion technologies, including plans to test a hydrogen engine demonstrator on a modified Airbus A380 testbed aircraft. But burning hydrogen inside a turbine engine is not as simple as swapping fuels. Hydrogen burns differently from kerosene. Engineers must solve issues of flame stability to ensure consistent combustion. Materials must withstand extreme temperature variations. Fuel systems must handle a gas that is highly reactive and prone to leakage due to its tiny molecular size. And while hydrogen eliminates carbon dioxide emissions during combustion, it does not eliminate atmospheric impact entirely. Water vapor released at high altitudes can contribute to contrail formation, which itself has climate effects. In laboratories, many of these engineering solutions already exist in controlled environments, but scaling them, making them reliable, certifiable, affordable, and deployable across a global commercial fleet is an entirely different challenge. Because building a prototype is one milestone, but reshaping the aviation industry at scale is the real challenge. So is ZeroE realistic? This program remains a bold and technically grounded vision, but one that faces steep realism hurdles in the near to medium term. When announced in 2020, Airbus set an ambitious target for entry into service by 2035, envisioning a regional aircraft around 100 passengers using hydrogen fuel cells to generate electricity for fully electric propulsion with only water vapor emitted. Yet the original 2035 timeline proved overly optimistic. By early 2025, the manufacturer delayed the program by 5 to 10 years, pushing likely entry into service to the late 20s or early to mid-2040s, with some sources pointing toward the 2040s or even late 2040s for full commercial scale. This adjustment came with a roughly 25% budget reduction, termination of certain sub-projects, including plans for A380-based in-flight fuel cell tests starting in 2026, and a clear acknowledgement from CEO Guillaume Faury that under current conditions, a hydrogen aircraft would not be competitive due to missing regulatory certification frameworks, immature technology maturation, and most critically, the absence of a widespread, affordable green hydrogen ecosystem. This contrasts sharply with SAF, which offers incremental decarbonization up to 80 to 100% reductions, depending on feedstock, and is already scaling, albeit slowly. Airlines can adopt SAF gradually without redesigning aircraft or rebuilding airports, delivering tangible emissions cuts today, while hydrogen remains a longer-term bet. The strategic debate is therefore clear. Airbus views hydrogen as potentially inevitable for truly zero-emission, longer-range aviation, where battery energy density falls short, and is willing to invest billions to lead the pathway, maintaining partnerships like hydrogen hubs at airports with over 220 stakeholders and advancing key tech despite setbacks. In short, ZeroE is realistic in the sense that the physics works, prototypes are progressing, and Airbus remains committed. Hydrogen-powered flight could become viable in the 2040 if the ecosystem catches up, but it's not realistic on the original 2035 schedule, and success hinges on massive coordinated global investment in green hydrogen production, infrastructure, and regulation. For now, it's a high-risk, high-reward, long-term play, rather than an imminent revolution, while SAF and efficiency gains handle the nearer-term decarbonization load. But in the end, regardless of whether ZeroE succeeds or not, Airbus will not simply be introducing a new product, it could be redefining the technological foundation of the next generation of commercial aviation. By moving first into hydrogen propulsion at scale, Airbus would position itself not just as an aircraft manufacturer, but as a central architect of aviation's energy transition. Airlines, airports, fuel suppliers, and even governments could find themselves aligning with Airbus-led standards, infrastructure models, and certification pathways. In that sense, ZeroE is not only about market share, it is about shaping the rules of the next era. But the stakes are equally high on the other side. Developing hydrogen aircraft requires billions in research and development, long certification timelines, and coordination across industries that traditionally move at very different speeds. If technological hurdles prove too complex, or if hydrogen infrastructure fails to mature in time, the financial cost could be enormous. Beyond money, there is reputational risk. A highly publicized sustainability promise that falls short could damage credibility in a market increasingly sensitive to environmental claims. Meanwhile, Boeing has adopted a more cautious strategy. Rather than betting on a radical propulsion shift, Boeing has focused on sustainable aviation fuel (SAF), incremental aerodynamic improvements, and next-generation efficiency upgrades within the existing jet fuel ecosystem. It is a lower-risk approach, one that leverages established infrastructure while gradually reducing emissions. What we are witnessing then is the emergence of two distinct philosophies. One path is evolution, improve what already exists, reduce emissions step by step, and minimize disruption. The other is revolution, redesign aircraft architecture, rebuild fuel infrastructure, and fundamentally change how flight is powered. ZeroE clearly represents the revolutionary path. It challenges not only how aircraft engines operate, but also how energy is produced, transported, stored, and distributed on a global scale. So perhaps the real strategic question is not simply whether hydrogen-powered aircraft can technically fly. It is whether the global aviation system from policymakers to power grids, is prepared to transform itself around that possibility.